So in the last video, we discussed a method of approximating the area between a curve and the x-axis. In particular, looking at that area between some finite portion of the x-axis, say between A and B. And the idea was chop the interval into a certain number of pieces. On each piece of the interval, build a rectangle that is as tall as the function is tall. So see how tall the function is tall at a point within each of your sub-interval regions. Build yourselves rectangles as tall as the function is tall, and well, you now have a way to estimate the area under the function. So let's bring that into a particular example. Here is the function x squared plus 1. We are going to approximate the area between this function and the x-axis between 1 and 3. And the number of subintervals here is going to be 4. So we're going to want 4 rectangles in total. So we say number of subintervals, this n equals 4, is really just the number of rectangles. And to be specific, because, well, in general, as we discuss this idea of estimating the area under a curve, you could pick any point within each subinterval. Here, for consistency's sake, let's make sure we're taking the left endpoint in each of the subintervals. So among all the values you could pick in the subinterval, pick the left endpoint each time. Figure out how tall the function is tall there, and use that to dictate the height of your rectangle. So let's deal with this situation. Now, who knows what this function looks like? Now, maybe you can imagine that this is a parabola shifted up 1 unit, but dismiss that from your mind for now. Let's just think abstractly about what is going on here. We are dealing with the interval between 1 and 3, and we have a function that has particular height at every point along the way. Plug in 1, you'll get something. Plug in 1.2, you'll get something. Plug in 1.5, you'll get something else. Plug in 2, you'll get something else. Plug in 2.5, you'll get something else. But here, what are we doing now? We are trying to build up rectangles, 4 in total, that are going to accurately assess the area under the curve. Now, how many rectangles? 4. Let's deal with that first. We have 4 rectangles. So what we need to do is figure out how wide each rectangle needs to be. Well, if the whole interval, figure out the total interval width. The total interval width is just 3 minus 1, which is 2. Well, if the whole thing is 2 units wide, and we need to chop it into 4 pieces, well then each subinterval is going to be what? It's going to be the total width divided by the number of pieces. In general, each piece, what? You have a total of 2 units of length. You want that divided into 4 pieces. So you take the total width of the interval divided by the number of pieces. That's going to give you this. I tell you what, let me write this out. Total width divided by number of pieces. And what's that going to give you? That's going to give you the width of each piece. Each subinterval width. Perfect. Okay, now, each subinterval width is 2/4 or 1/2. So the next point is going to be at 1.5, the next point is going to be at 2, and the next point is going to be at 2.5. And what do you know? It works out perfectly, right? Because you can see, based on when we walk a half unit in each, for each step, we have ultimately broken this original region into 4 subregions. So you can see the 1, 2, 3, 4 subregions. Now the question is, because we know that each of our regions is a 1/2 inch wide, the question now is, how tall do we have to build each of our rectangles? And to answer that question, we need to build them as tall as the function is tall. Now, where are we going to look between 1 and 1.5? Because we could go up as far as the function goes up at any point between 1 and 1.5. What point are we going to pick? Well, remember, the problem suggested that we use our left endpoint to build each rectangle. So, among all of the possible, and there are infinitely many possible numbers, of course, right, between 1 and 1.5, and among all those possible numbers, we're going to choose the left endpoint to do it. So we need to figure out what f of 1 is to figure out this height. But ultimately, long story short, this first rectangle is going to be f of 1 units tall. That's not its width. Its width is 0.5, right? Because, well, you can see that from how we took the interval of like 2 and chopped it into 4 pieces. You can see that that's between 1 and 1.5. But the height, how tall this thing is, it's going to be f of 1 tall. How tall is the next rectangle going to be? The next rectangle is going to be as tall as the function is tall at 1.5. Why 1.5? Because we use the left endpoint to build each rectangle. So what is the left endpoint between 1.5 and 2? The left endpoint is 1.5. So this rectangle is going to be f of 1.5 tall. Next subinterval, we're looking between 2 and 2.5. We can pick any of those points and plug it into our function and figure out how tall the function is there. But we don't want to build up our rectangle to any of those points. There's infinitely many to choose from. We want to choose the left endpoint because that is sort of the directive that was given to us. So okay, let's use the left endpoint to build the rectangle. So between 2 and 2.5, we need a rectangle. We're going to build off of the left endpoint here. The left endpoint is at x equals 2. The height of that is going to be f of 2. However tall f of 2 is, I'm not even sure. I'm just drawing this abstractly. I mean, we could be sure. We could plug it into our original function. We'd find out that f of 2 is 5, whatever. But the long story short is that rectangle is going to be as tall as the function is tall at the point x equals 2. And next, 2.5. Well, why 2.5? Because we're looking on this next region. We need a rectangle here. We need to build this. We know how wide the rectangle is. It's going to be 0.5. How tall is the rectangle going to be? Well, it's going to be as tall as the function is tall at some point in between. But we don't want to pick any point in between because we're working here with left endpoints. So the left endpoint is going to be 2.5. And however tall the function is at 2.5 is going to dictate the height of this rectangle. So this rectangle will be f of 2.5 tall. And now, what is the total approximate area going to be? The total approximate area is going to be the sum of the areas of the 4 rectangles. So the first rectangle is a half times f of 1 plus a half times f of 1.5 plus a half times f of 2 plus a half times f of 2.5. Here is the area of the first rectangle, and the second, and the third, and the fourth. The total area of the rectangles is just base times height, base times height, base times height, base times height, 4 times over in this case, because we had 4 rectangles. And now we just need to compute what f of 1, f of 1.5, f of 2, and f of 2.5 is, but that's no sweat because we know what our original function is. So let's just run those numbers, right? F of 1, 1 squared plus 1, that's 2. F of 1.5, that's going to require, I suppose, a little bit of computation, but 1.5 squared plus 1. 1.5 squared is 2.25. You can do that in a calculator, of course, right? Plus 1, that's going to be 3.25. So we already know that f of 1 is 2. Let's plug that in. And f of 1.5 is 3.25. And now, what about f of 2? F of 2, that shouldn't be very difficult to compute because that's a whole number. 2 squared plus 1, that's going to be 4 plus 1, that's going to be 5. And now the next one's going to be a little bit trickier to compute because we got to do f of 2.5. But that's just going to be 2.5 squared plus 1. 2.5 squared, you can go to a calculator, right? 6.25 plus 1, plus 1, 7.25. Okay, 7.25 is the function value at 2.5. And now, all we have to do is run the numbers here. So a half of 1 is 1. A half of 3.25 is 1.625. A half of 5 is 2.5. A half of 7.25 is 3.625, excuse me. And, well, long story short is now we just have to add these numbers together. What is 1? 1 is the area of the first rectangle. Why? It was half a unit wide and 2 units tall. What's 1.625? That's the area of the second rectangle. Why? Because it was a half unit wide and 3.25 units tall. What is 2.5? That's the area of the next rectangle because it was a half unit wide and 5 units tall. Look, I drew this picture crappy in some sense precisely. I drew it crappy because the function was higher at f of 2 than it was at f of 1.5. But that doesn't matter in terms of my picture because my picture captured the essence of what was going on exactly. It was 4 rectangles of certain heights with certain widths, and those heights and those widths were transmitted to our equation, and now we run the numbers. yeah, and the long story short is if we just add these things up, and I mean, I suppose I could try to do this in my head, but I kind of don't want to right now, so let me just add this up. 1 plus 1.625 plus 2.5 plus 3.625, boom, 8.75. Now, is 8.75 precisely the area that is under our function between 1 and 3? Well, probably not, right? Because our function is going to be curvy. In fact, our function is going to be a parabola. It's going to curve the entire way along its path. But these rectangles are going to get us close to the area under the curve, and since we're looking for an approximation, this will do it.